Hey, Grade 9, welcome to today's Explainer. Let's get right into it because we're looking at the invisible rules that literally govern everything around us. Have you ever wondered why a rolling ball eventually just stops? Or how a massive rocket actually manages to get off the ground? Well, it's not magic. It's science. Today, we're unpacking exactly how forces affect motion. So grab your notebooks because you're about to see the whole universe in a totally different way. Here's a quick look at our agenda for today. 1. Introduction to forces. 2. The friction factor. 3. Newton's first law. 4. Newton's second law. 5. Newton's third law. And finally, a summary and exam prep. Starting right at the top, Section 1. Introduction to forces, pushes, pulls, and everyday motion.
Let's ground this abstract science with something you've definitely experienced. Think about a soccer ball sitting in the grass. When it's just sitting there, it's completely at rest. It is absolutely not going to move until someone applies a push to it, like a kick. That push, that's what we call a force. Basically, a force can make an object start moving, speed up, slow down, change direction, or even change its physical shape. Kind of like when you squeeze a lemon. It's the root cause behind any change in motion.
Now, for your exams, you'll need the official definition. A force is a physical quantity. And here's the crucial part. It requires both a magnitude, which is just a fancy word for its strength, and a direction. You can't just say, I applied a force of 10. Nope, you got to say, a force of 10 pulling to the left. Oh, and definitely write this next part down. The standard unit of force is the Newton. When you write it out as a full word, use a lowercase n, but its symbol is always a capital N.
So how do we actually measure that force in the lab? We use something called a spring balance. If you hang an object from it, the internal string stretches out. But what is it actually measuring? It's measuring the gravitational force, literally the Earth pulling down on that object. And that downward pull is exactly what we call weight.
In the real world, there is usually way more than one force acting on an object at the same time. Picture a massive game of tug-of-war. If both teams are pulling with the exact same strength but in opposite directions, the rope doesn't go anywhere, right? Those are called balanced forces, which means the overall net force is a big fat zero. But the second one team pulls even slightly harder, boom, the forces become unbalanced. The net force is now greater than zero and the rope starts accelerating toward the winning side. Motion only ever changes when forces are unbalanced.
Let's do a quick pause and ponder to test this out. Picture a basketball just floating in a pool. It's bobbing there, not really moving. So what forces are acting on it? Think about it for a second. Well, Earth's gravity is definitely pulling it down, but the water is actually pushing back with an upward force, which we call buoyant force. And since the ball isn't sinking to the bottom or flying up into the sky, those two opposite forces are perfectly canceling each other out. They are totally balanced.
All right, moving right along to Section 2, the friction factor, the invisible force.
Let's talk about a force that constantly tricks our brains. Imagine a little tabletop experiment. You stack 4 coins and flick them across a desk using a rubber band. If you do this on a slightly rough wooden table, the coins go a little bit and then just stop. But if you do the exact same flick on a super smooth marble floor, those coins slide way, way further. Why's that? I mean, the rubber band applied the exact same force both times, right? The invisible culprit here is friction. Friction is a force that happens between two surfaces in contact, and it literally always opposes motion. The rougher the surface, the stronger the friction. Now here's a huge misconception. People used to think objects just naturally wanted to stop moving. But back in the 17th century, a scientist named Galileo realized something mind-blowing. He theorized that if you could somehow completely turn off friction, a moving object would just slide forever. It doesn't want to stop. Friction is forcing it to stop.
Okay, now for the main event. Section 3, Newton's first law, the law of inertia. Building on Galileo's ideas, Sir Isaac Newton came up with 3 definitive rules.
Let's look at the first one. An object at rest remains at rest, and an object in motion continues to move with a constant velocity unless a net force acts upon the object. Trust me, you're going to want to memorize that exact phrasing for test day. It's also called the law of inertia. And honestly, inertia is really just a scientific word for an object's stubbornness. If a rock is sitting still, it stubbornly wants to stay still. If it's flying through space, it stubbornly wants to keep moving in a straight line forever, unless an unbalanced force rudely interrupts it.
Which brings us to Section 4, Newton's second law, mass, force, and acceleration.
So, what exactly happens when an unbalanced force does interrupt an object? The second law tells us that when a net force hits an object, it accelerates. Pretty straightforward. Push harder, it accelerates faster. But the more mass the object has, the heavier it is, the less it's going to accelerate from that same push. Think about catching a really fast cricket ball or baseball. You naturally pull your hands backward as you catch it, right? Why? Well, by increasing the amount of time it takes to slow the ball down, you're decreasing its acceleration. And doing that dramatically reduces the force that hits your hands. Basically, it hurts way less. And that perfectly sets up the golden formula of physics. F equals ma. Force equals mass times acceleration. This one tiny equation explains so much. It proves why pushing a massive truck requires a monstrous amount of force, but flicking a tiny pebble to accelerate at the exact same rate requires almost nothing. Let's actually put this to the test with a grade 9 exam scenario. Picture a weightlifter holding a barbell perfectly steady over their head. The bar itself is 10 kilos, and let's say there's 10 kilos on each side. So the total mass, our m, is 30 kilos. Now gravity is pulling that whole thing down with an acceleration of 9.8 meters per second squared. To find the downward force, we just multiply the mass, 30, by the acceleration, 9.8. That gives us 294 newtons. So to keep that barbell from crashing down to the floor, our weightlifter has to push up with an exact, perfectly balanced force of 294 newtons.
All right, home stretch. Section 5, Newton's third law, action and reaction.
This is where we see some incredible symmetry in the universe. The third law states, whenever one object is exerting a force on a second object, the second object is simultaneously exerting an equal and opposite force on the first object. In plain terms, every single action has an equal and opposite reaction. If object A pushes object B instantly pushes back on object A with the exact same strength, just in the reverse direction.
Think about someone paddling a canoe. It is the perfect example of this. To move forward, the paddler pushes the water backward with their oar. That is the action force. And in response, the water doesn't just sit there. It exerts an equal and opposite reaction force, pushing the paddle, and therefore the whole canoe, forward. Literally, the harder you shove that water backward, the harder the water shoves you forward. It's brilliant.
And just like that, we're at Section 6, Summary and Exam Prep, Mastery Check.
Okay, let's lock this in so you absolutely crush your exam. Here are your rapid-fire revision tricks. First law, think inertia. Objects are stubborn. Second law, think F equals ma. That's your core math rule for calculating force. And third law, think action and reaction. Forces always come in pairs.
Let's wrap up with a classic multiple-choice question. If no net force acts on a moving ball on a perfectly smooth, frictionless surface, does its velocity A, increase, B, decrease, or C, remain the same? Got your answer? If you picked C, remain the same, you nailed it. Because of Newton's first law, without friction to slow it down, that ball is just going to keep rolling forever. Isn't it kind of mind-blowing that every single movement in the universe, from a basketball bouncing on a court to literal planets orbiting the sun, is governed by these exact same 3 rules? Keep an eye out today and see what everyday motions you start looking at totally differently. Keep questioning, keep observing, and I'll see you on the next explainer.